Hello APC Mechanics students, today we'll solve the past paper of RQ 2016, exercise number 3. A uniform rod of length D has one end fixed to the central axis of a horizontal frictionless circular platform of radius r is equal to 2d, as shown here. The block is set in frictionless groove so that it can only move along the radius of the platform. This block can move along the centripetal direction as shown here, and there is no friction. So notice the following. This is very important. They have mentioned figure 1, so only restrict yourself now to figure 1. Don't look at figure 2. Okay? So whenever they mention figure 2, we're gonna look at figure 2. The equilibrium length of the spring is d over 2. This is extremely important. Why? Because we should know the equilibrium length of the spring, because whenever there's a spring, it means we need to apply Hooke's law. Because this is an ideal spring, so the force would be kx and the energy would be half kx squared. Now what does x? X represent the elongation or compression of the spring. So till this moment d over 2 won't enter anything in Hooke's law, because this is the equilibrium length, this is the free length. Below is a table showing the mass of the block and the masses and rotational inertia of the rod and the platform. So we have the masses of the three bodies, and we have the rotational inertia for the rod and the platform. The rotational inertia of the block is not given. If the block is considered as a particle, we know that the rotational inertia of a particle is given by mr square, where r is the radius, or the distance from the center of rotation. A motor begins to slowly rotate the platform counterclockwise as viewed from above until the platform reaches a constant angular speed omega. Under these conditions, the spring has stretched by an additional length d over 2 as shown in figure 2. Now they mentioned figure 2, so we can use it. So initially, and remember this is a horizontal configuration, so these two figures are top view. Then we cannot represent easily the pull of gravity in this case of the block. The pull of gravity would be represented down into the page. So it would be down like that, and the normal push would be up out of the page, and they cancel each other because remember this is a horizontal configuration. Now there is a motor installed to this platform which provides energy, so the platform will start to rotate after achieving a certain constant angular speed omega. Remember that this is the free length of the spring. Now the spring elongates by distance d over 2, and given that the radius of the platform is given by the double of d. Now they're telling us derive an expression for the spring constant of the spring. So basically, let me repeat the statement. Answer the following questions for the platform rotating at a constant angular speed omega. Express all your answers in terms of md, omega, and physical constants as appropriate. Now we need to derive the physical constant, the spring constant of the spring in terms of md and omega. That's good, because now under rotation, okay, we have the pull of gravity and the normal push, but you can forget about them because they cancel. This is a horizontal configuration and there is no friction. Now what are the forces that are acting on the block? We have the force of the spring, which is toward the center, and this can be equated by mv square over r. V is related to omega because this is a centripetal motion, and indeed we can determine or relate k to omega. Now the thing is that now we will say that Fs is given by kx because this is an ideal spring. Now what does x represent? X is the elongation of the spring, which is basically d over 2 and not d, alright? And moreover, if the centripetal acceleration is given by v square over r, what does r in this case represent? R is the distance from the object itself to the axis of rotation. Now if the length of the rod is d, so let me write here d, then in this case the distance from here to here would be the double of d. Then now I have set for you all the ingredients that allows us to derive the expression for the spring constant, and this is determined by a big law, which is Newton's second law. So let me write apply Newton's second law. Which is given by F naught is equal to ma. Now we have the pull of gravity plus the normal push on the block plus the force of the spring, that would be equal to ma. and indeed the mass of the block is given by m. Now this is a vector equation. We need to project it along a certain direction, which is basically the centripetal. Then projection. Along the centripetal direction. Now these happen to be along the vertical, which is independent of the centripetal, so that would be 0 plus 0. Now we have the force of the spring. Is it positive or negative? Notice that the force of the spring is pointing toward the center, and in centripetal direction always the center is toward the center is the positive direction. That would be Fs is equal to m. A has been projected along the centripetal, so that would be AC. Now this is an ideal spring, then that would be Kx is equal to m v squared divided by r. Let me justify again what does x and r represent. X represents the elongation of the spring. Initially the spring is given by d over 2. Its elongation now it's given by d over 2, so let me write here that would be k d over 2 m. Okay, before I replace the value of r, so let me say that v is equal to r omega. Then that would be r square omega square divided by r. Now this would cancel, and k d over 2 is equal to m omega square multiplied by r. What does r represent? R is the distance of from the object to the axis of rotation, which is basically given by the double of d. Then let me write here k d over 2 is given by m omega square, the double of d, and we're interested in searching for the value of k. D with d would cancel, then indeed k would be given by 4 m omega square. So that represents the stiffness of the spring in terms of the given. So keep that in mind, because this will be replaced probably on later, because this is a constant that has been determined in terms of the following quantities. Now in part B, idea 1, determine an expression for the rotational inertia of the block around the axis of the platform. As we have mentioned at the beginning of the exercise, that the block is a particle and the rotational inertia of the particle is given by m r square. R represents the distance from the block to the axis of rotation. Then again, this is m, the double of d to the power of 2, which is basically 4m d square. And this requires no law. Then I will say that the rotational inertia of the block is given by m r square, and that would be m multiplied by 2d to the power of d to the power of 2, and that would be given by 4m d square. Then indeed the rotational inertia of the block solely is given by 4m d square. Now in idea number 2, they're telling us to derive an expression for the rotational inertia of the entire system about the axis of the platform. What does the system represent? The system represents of 3 different bodies given by the block, rod, and the platform. So we need to add the rotational inertia for all of these together. Now the rotational inertia of the rod is given by mr d square over 3, and that would be mpr square over 2, and the masses are given in the second column of the table. Although they have mentioned derive, but this requires no law, then I total of the system would be I for the block plus I of the R for the rod plus I of the platform, which is given by P. Now I of the block is given by 4md square, and I of the rod is given by mrd square over 3. And I of the platform is given by mpr square, but what does R represent? R is the double of D. So I think over 2. Now that would be 4md square. Now the mass of the rod is given by a triple of m. Now 3 with 3 would cancel, plus the mass P is given by 5, I think, yes. And R is given by the double of D to the power of 2 divided by 2. Now we can factor out md square, and here we would left with 4, that would be 1, and 4 multiplied by 5 divided by 2, that would be 10, which is given at the end 15 md square. Then the rotational inertia of the system is given by 15 md square. Determine an expression for the angular momentum of the system about the axis of the platform. Now let's double check. Indeed, they're telling us to express our answers in terms of md omega. Then this is good so far, also for I of the block and I for the system. Now the angular momentum for a rigid body is given by L is equal to I omega. Omega, we're gonna keep it the same because it's an allowed physical quantity. I would be replaced by 15 md square, and that would be multiplied by omega. Then the expression of the angular momentum of the entire system is given by 15 md square multiplied by omega, and this requires no law. It's just the definition. Now in what follows, they're telling us while the system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned on the axis as shown in figure 3 above. This is important, until the center of the rod. If you remember carefully, this is the rod and the length of the rod is given by d. Now if the pivot becomes completely at the center of the rod, then this distance here, which is not indicated on the figure as a trick, so that would be d over 2, and the free length of the spring is given by d over 2. Now, so this is d over 2, and now the new elongation or compression of the spring is given by x, basically the elongation. The same constant angular speed omega is maintained by the motor driving platform. Although here the pivot, the position of the rod has changed with respect to the pivot, so probably you think that the disc will change in speed. But the thing is that the mechanism in the motor will work in a way such that omega would remain constant. Now in part D, they're telling us derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3 above. So we need to determine the expression of x. So again, this can be determined using Newton's second law. And we know that, so no need to repeat all of this steps here. We can directly start from the force of the spring is equal to MAC. And remember that we need to derive our expressions in terms of MD and omega. Now the force of the spring in this case is given by the spring constant K, and the elongation of the spring, in this case the elongation of the spring is given by X, is equal to the mass multiplied by V square, and V square, if you remember, V square over R, that would be omega square R square divided by R, which is basically omega square multiplied by R. Now we're interested in determining the value of X. M is an allowed quantity, omega is an allowed quantity, but however K and R should be converted in terms of the given quantities MD and omega. And if you remember from part A of this exercise, K has been determined in terms of these, and it's given by 4m omega square. Then indeed that would be 4m omega square x that we wish to determine is equal to m omega square. Now what does R represent? Because distances have changed. R represents the distance from the pivot or the axis of rotation to the mass, and that would be d plus x. Now we can apply the cancellation effect. Then 4x is equal to d plus x. Now what's the type of this equation? This is a linear equation. Then 3x is equal to d, which makes it that x is d over 3. Now for parts E, F, and G, assume the center of the rod is still moving toward the axis of the platform. So here what's happening is that the pivot, the rod, the center of the rod is still moving toward the axis of the platform. So basically this is just moving down, okay? Now in part E, is the angular momentum of the entire system increasing, decreasing, or staying the same? Now the angular momentum here is given by I multiplied by omega. Now I consists of three parts: I for the block, I for the platform, and I for the rod. Now I of the platform, it's not changing because nothing is changing with the platform. Now the rotation inertia of the block is decreasing because the block is coming closer to the center, and we know that whenever, so inertia is about mass distribution, and because the block is coming closer to the center, then this I of the block would decrease. Now what would happen also for I of the rod? Remember that the center of the rod in this case is still moving toward the axis of the platform, which means also the mass of the rod is getting closer to the axis of rotation, which means that the mass distribution is getting closer to the axis of rotation, which makes the rotation inertia decreases, which makes the angular momentum in this case decreasing, taking into consideration that the mechanism of the motor is providing a constant angular speed. Then let me here in this case justify and say that since the rotational inertia decreases, then since the rotational inertia decreases while the angular velocity remains the same, then the angular momentum of the entire system decreases. Now part F, this is a tricky question. They're telling us in order to keep the system rotating with a constant angular speed omega, is the motor doing positive work, negative work, or no work on the rotating system? Now this can be understood by the work energy theorem. Remember that the work energy theorem is given by delta K is equal to the work done by all the external forces. So let me say here the only external force providing work, or the only external torque which is providing work, is the work done by the motor. Now here we have mentioned that the rotational inertia decreases and kinetic energy is about half I omega square. Then if I decreases, then the kinetic energy is decreasing. So basically what's happening to the disk while it's rotating, even though it's rotating at a constant angular speed omega, we suppose, but the kinetic energy, which also depends on the rotational inertia, is decreasing. So let me write again that delta K is equal to the work done by the motor. So because I decreases and the kinetic energy is about half I omega square, then I decreases as well, which means the variation in the kinetic energy is negative due to this decrease. So this is negative, then this is negative. Therefore, the work done by the motor is negative. Then let me say, since the rotational inertia decreases, then the rotational kinetic energy of the system is decreasing. Then according to the work energy theorem, the motor is doing negative work. And now moving on to the next page, which is the final part of this exercise. They're telling us part G on the block in figure 4 below, draw a single vector representing the direction of the acceleration of the block. Draw the vector so that it's starting on and pointing away from the block as for the instructions of an FED. Now we know that because this is a circular motion, then part of the acceleration would be toward the center. So one component of the acceleration should be down. But now if you notice carefully in the previous part, there's something important that we have discussed, is that the motor is providing negative work. And the work done by the motor is basically the torque times the displacement, which is theta or delta theta. If this is negative, and let's assume that the displacement is positive, which means the torque provided by the motor is negative. And whenever the torque provided by the motor is negative, which means there is a tangential acceleration acting on the particle which is negative. So there is also part of the component which is backward. Now, although the mechanism here is working in such a way that to provide constant angular speed, but it's more complicated than that, because if you remember here carefully in this statement, there's something that they have mentioned, that the center of the rod is still moving toward the axis of the platform. So also you need to take into consideration the thing is that this is moving closer. However, we know that part of the acceleration would be toward the center, but also you should take into account the torque done by the motor, which is providing an acceleration in the negative direction if this is the direction of rotation. So in this case, the acceleration would be pointing down to the right. So that would be the acceleration of the block. And let me represent it as a vector. And that's it for me in this video, guys. See you soon in a new one.